All right, honors chemistry kids, we are going to do limiting reagents today. So limiting reagents are basically stoichiometry with the caveat that we are starting with X number of something and Y number of something for our reagents, and then trying to figure out which of our reagents we run out of first. A lot of us have done this when we've tried to cook something in the kitchen. We'll go into the refrigerator or the pantry and we'll try and make, for example, chocolate chips. We'll have some butter, some flour, some eggs, some chocolate chips, whatever, and try and make some chocolate chip cookies. And sometimes we don't have enough to do a whole batch. So we might have to half our batch or whatever. We might only have a cup of chocolate chips instead of 2 cups of chocolate chips. So we have only enough to make a half batch. That cup of chocolate chips is what limits us or limits how much we can make. So a limiting reagent or limiting reactant, it's sometimes called, is the reactant or the reagent that we start with that we run out of first. So let's do a little example here. I've got some tools here. I've got some screwdrivers, and I've got some pliers, and I've got some hammers, and I want to make toolkits. Okay, so for each toolkit, I want to have 2 screwdrivers, and I'm assuming they're going to want a Phillips and a flathead screwdriver, a wrench, or sorry, not a wrench, a plier set, and a hammer. So let's figure out how much we can make from each thing. So if I look at my hammers, I have how many hammers? I have 4 hammers. So I can make 4 toolkits with the hammers that I have. If I look at my wrenches, I have 5. So I'm going to be able to make 5 toolkits with the pliers that I have. And then if I look at my screwdrivers, I have 10 screwdrivers, and I wanted 2 screwdrivers in each kit. So that allows me to make 5 kits. So with my hammers, I can make 4 kits. With my pliers, I can make 5 kits. And with my screwdrivers, I can make 5 kits. So what I'm going to run out of first is my hammers. My hammers are my limiting reagent. Because they're the thing that stops me from making that 5th kit. I will have extra pliers and screwdrivers left. Okay, so this is basically just stoichiometry, where we play out the math with both reagents and see which one makes us the fewest or the fewer amount of things. Okay, so here's another example. A student adds 0.75 moles of aluminum wire to a beaker with 0.8 moles of hydrochloric acid. How many moles of aluminum chloride will be produced? So the very first thing, like we did with stoichiometry, is we always have to start with a balanced chemical equation. So let's look at what we're dealing with here. We have aluminum wire. Aluminum wire is just going to be aluminum. And we're using hydrochloric acid. That hydro means that it's a binary acid. So I know I have hydrogen and chlorine. Hydrogen is a positive 1. Chlorine is a negative 1. So I know I'm going to need 1-to-1 ratio here for hydrochloric acid. Okay, now the thing is, how do I predict the reactants? If I remember, aluminum is a +3, hydrogen is a +1, and chloride is a -1. So remember, positives replace positives and negatives replace negatives. So that means that the aluminum and the hydrogen being both positive, they're the ones that are going to switch. Okay? So my aluminum is a +3, so chloride is a -1, so I'm going to need 3 chlorides there. And remember, when hydrogen is by itself, it is our diatomic gas. It's one of our Brinkelhoff or our diatomic gases, so it's going to be in groups of 2. So there's my skeleton equation. Now I need to go back and balance it. So let's look at aluminums. I've got one aluminum. I'm okay here. One hydrogen, two hydrogens. So let's put a 2 here. I've got 3 chlorines, and here I've got 2 chlorines. What's the least common multiple between 2 and 3? It's 6. So to get 6 chlorines, I'm going to need to multiply this by 6. To get 6 chlorines, I'm going to need to multiply this by 2. Okay? So let's recheck this. So one aluminum, whoops, I need to go back. There we go. We need to go back and check the aluminum. So 2 aluminums, 6 hydrogens. Oop, I'm going to need to do this. 3 here, 6 chlorines, 6 chlorines. Okay, always go back and double check. Okay, so we have 0.75 mole of aluminum and 0.8 mole of hydrochloric acid. We're going to take them one by one. So if I have 0.75 moles of aluminum, remember stoichiometry, I'm going to look at aluminum in relationship to aluminum chloride. So I'm going to look at my coefficient here with my coefficient here. So I have a ratio of 2 aluminum moles to 2 aluminum chloride moles. Okay, so my moles of aluminum I want to cancel, so I'm going to put my 2 moles, 2 moles of aluminum down here, and then 2 moles of aluminum chloride here. Okay, so 2 divided by 2 gives us 1. So this essentially will give me 0.75 moles of aluminum chloride that I can make. I can't write today. Okay, now we need to do the same thing, but now we're going to start out with 0.8 mole of hydrochloric acid. So if I have 0.8 moles of hydrochloric acid, I'm going to grab that coefficient from the equation. So if I look at hydrochloric acid, I have a 6 here in relationship to this 2. Okay, so 6 moles of hydrochloric acid react to make me 2 moles of aluminum chloride. Okay, so 0.8 divided by 2 divided by 6 is 3, right? 1/3. So 0.8 divided by 3 will give me, my calculator will spit out this. I really only have 1 sig fig, so let's call that 0.3 moles of aluminum chloride. So now the thing that we have to do is we've got to compare. We've got to compare this number to this number and see which one is smaller. We are always going to look for the smaller. Come on. The smaller is the one that is going to be our limiting. So what is limiting for us? It's the hydrochloric acid. Yay. So hydrochloric acid is what is limiting. We can only make 0.3 moles of the aluminum chloride. Once we get to 0.3 moles, really 0.27 moles of aluminum chloride, that reaction is going to stop because we don't have any more hydrochloric acid to react. We're going to have aluminum wire left over. Okay? So we will have aluminum wire left over. Kind of like these tools up here that were left over, we're going to have extra aluminum. Okay, let's look at example 7. One of the few xenon compounds that can form is cesium-xenon heptafluoride. So cesium with xenon and 7 fluorines. How many moles of cesium-xenon heptafluoride can be produced from the reaction of 12.5 moles of cesium fluoride with 12 moles of xenon hexafluoride? So here we have our equation. The The first thing to do is to check to make sure it's balanced. Is it balanced? Let's look at it. We've got 1 cesium and 1 cesium. We've got 1 plus 6, so 7 fluorines here, and we've got 1 xenon and 1 xenon. So we're okay. It is balanced. Okay, so now what we're going to have to do is we're going to have to do the stoichiometry for both of these numbers. We're going to play out 12 moles of cesium fluoride and 10 moles of xenon hexafluoride. So here we go. You probably have a pretty good idea already. So if I start off with 12.5 moles of cesium fluoride, we're going to grab, oh, that 1 is terrible. We're going to grab our coefficients here. So I have 1 cesium fluoride making 1 cesium xenon heptafluoride. So 1 cesium fluoride, 1 mole of cesium fluoride reacts to make 1 mole of cesium xenon heptafluoride. So that means I will be able to make 12 divided by 1 times 1 is 12.5 moles of cesium xenon heptafluoride. Okay, now to do the same thing with the 10 moles of xenon hexafluoride. So if I start with 10 moles of xenon hexafluoride, once again, my ratio, I've got 1 mole here to 1 mole here. So 1 mole of xenon hexafluoride will react to make 1 mole of cesium xenon heptafluoride. So 1 times 10 divided by 1 is still 10. So I can make 10 moles of cesium xenon heptafluoride. Okay? So, like I said before, we are always going to look for the smaller of the two, because the smaller of the two is where we run out of something. So the smaller of the two is this. So that means xenon hexafluoride is my limiting reagent. So I run out of stuff. So this is my limiting. Xenon hexafluoride is limiting. Okay? I can only make 10 moles of cesium xenon hexafluoride or heptafluoride. Okay? Let's go on to my next example. So, example 8. The reaction between solid sodium and iron 3 oxide is one in a series of reactions that inflates the automobile airbag. I don't know if you knew that, but this is one of the reactions that we have going on. And this, we have one of the biggest airbag manufacturers just up the road here in Utah, up in Ogden. It's called Autoliv, and there are a lot of engineers that work there and chemists as well to create these reactions to inflate the airbags. So we have 6 sodiums reacting with rust, iron 3 oxide, creating sodium oxide and solid iron. This reaction puts off a lot of heat. So if you've ever been in a car accident where the airbag has deflated, there are also chemicals in there that will cool this down a little bit so it doesn't burn you. Okay, so if I start off with 100 grams of sodium and 100 grams of iron 3 oxide are used in the reaction, we want to determine 3 things. We want to determine what's limiting, what is in excess, and the mass of solid iron that we are going to produce. So once again, we're going to do the stoichiometry with 100 grams of sodium and 100 grams of iron 3 oxide and see how much iron can be produced. So here's the stoichiometry here. So if I start off with 100 grams of sodium Now, remember, I'm going from grams to moles of the unknown, back to grams of the unknown. So I have to use my molar mass. So if I look on my periodic table, let's look at my periodic table really quick. Why does this not want to open? We have our honors chemistry, and let's get our periodic table up. If I look at sodium, sodium has a molar mass of 22.99. So that's what we're going to use here. So I have 22.99 grams of sodium in 1 mole of sodium. Okay, there's my first step. So I've gone from grams to moles. Now I need to go to moles of what I want to know. And I'm going to do that using the coefficients of the balanced equation. So I have 6 moles of sodium. And once again, that pen did not transfer over quick enough. 6 moles of sodium reacting to make me 2 moles of iron. I want my moles of sodium to cancel out. So I'm going to put moles of sodium on the bottom in the next step. So I have 6 moles of sodium reacting to make me 2 moles of iron. Okay, so I've gone from moles of what I know into moles of what I want to know in that step using the coefficients from the balanced equation. Okay, my next step now is to use the molar mass of iron to go from moles of iron into grams of iron. So let's look at our periodic table. So if I look at iron, I have a molar mass of 55.85. So that's what we're going to use. So in 1 mole of iron, I have 55.85 grams of iron. Okay? So you're going to want your handy dandy calculator. So we're going to take 100 divided by 22.99 times 2 divided by 6 times 55.85. And we come out with 80.98 grams with our sig figs. 80.98 grams of iron are produced. Okay. Now, notice we have 4 sig figs here, so we're going to have 4 sig figs. Now we get to do the same thing with our 100 grams of iron 3 oxide. So 100 grams of iron 3 oxide, and I need to find my molar mass of iron 3 oxide. So we just said that iron was 55.85 grams per mole. We've got 2 irons and we've got 3 oxygens. So let's add that up. And oxygen, if you remember, let's take a gander. It's 16.00. So 2 times 55.85 for the irons plus 3 times 16 for the oxygens. That gives us a molar mass of 159.70 grams per mole. Okay, so I've done my first step. Now I want to do my mole to mole using my coefficients in my balanced equation. So if I look at iron and iron 3 oxide, I have 1 iron 3 oxide for every 2 irons in this equation. So if my computer will let me write, here we go. So I have 1 iron 3 oxide, one mole of iron 3 oxide gives me 2 moles of iron. And then my last step is to go from moles of iron into grams of iron. So 1 mole of iron is 55.85 grams of iron. And when I do all of that math with sig figs, I get 69.94 grams of iron are going to be made. Okay, Now, the thing that we have to look for is which one is smaller. Hopefully you noticed that the one that is smaller is this one, okay? So that means our iron trioxide is our limiting reagent. Let's actually do this in green. So for question A, our limiting reagent is our iron 3 oxide. The reactant or the reagent in excess, or one that we are going to have extra, is going to be our sodium. So sodium is our extra. Now, the amount that we can make is this. We can make 69.94 grams of iron. Okay? So that is how you attack this. Now, number 9 is a little bit more involved. We're not going to just ask what the limiting reagent is and what the mass that can be produced. I want to know the percent yield, and I want to know how much excess is remaining. Okay, so these are a couple more skills that we can use with our limiting reagent and with stoichiometry. So here we go. Lithium reacts spontaneously with bromine to produce lithium bromide. So the first thing we've got to do is write a balanced equation. So we're going to start with lithium. Lithium is our metal. And if you remember, bromine is one of our Brinkelhoff gases. So it comes in groups of 2. And lithium is a +1, and bromine is a -1. So they're going to go together on a 1-to-1 basis, 1-to-1 ratio. So we will have lithium bromide. Now, what we have to do now that we've got our skeleton is to go back and balance. So I need to double this to get 2 bromines, which means I need to go back and double my lithium bromide, or my lithium right here. So there's my balanced equation. Okay, now the next thing is we've got to do the stoichiometry twice. 25 grams of lithium and 25 grams of bromine. Okay, so let's start with our 25 grams of lithium. So if I have 25, that pen did not want to switch over quickly. 25 grams of lithium. I want to go from grams to moles. So I need to look up my molar mass of lithium. So lithium is 6.94. So I have 6.94 grams of lithium in 1 mole of lithium. Then my next step is to use my molar ratio for my balanced equation. I have 2 moles of lithium to create me 2 moles of lithium bromide. So 2 moles of lithium will create 2 moles of lithium bromide. And then the next thing is to go from moles of what I want to know into grams using the molecular mass. So in 1 mole of lithium bromide, okay, let's see, lithium we already said was 6.94. Bromine, let's look up bromine. Bromine is 79.90. 79.90. So when we add that together, we get 86.84 grams per mole. So we're going to use that. So 86.84 grams of lithium bromide. Now I've got 3 sig figs here. So when I do the math, I'm going to take 25 divided by 6.94, multiplied by 2 divided by 2, or you could just skip over that because it reduces to 1, multiplied by 86.84. That will give me 313 grams of lithium bromide. Okay, that R needs to be better. Now I get to do the same thing all over again with my 25 grams of bromine. And once again, my pen did not switch very quickly. So 25 grams of bromine. Now remember, bromine is diatomic. There's 2 bromine atoms together. So I'm going to have to take that 79.9 and multiply it by 2 to get 1 mole of bromine because it's Br2 for my molecular mass. So 79.9 times 2 gives me a mass of 159.80 grams of bromine for 1 mole of bromine. Okay, don't forget to multiply it by 2 because it's diatomic. My next thing, I've gone from grams to moles. Now I need to go from moles of what I know to moles of what I want to know using my mole ratio. I have 1 mole of bromine. And I'm going to put bromine on the bottom because I want it to cancel out, reacting to give me 2 moles of lithium bromide. Okay, so I've used my ratio to go from moles of what I know into moles of what I want to know. And then my last step is to use the molar mass to get back to grams. So 1 mole of lithium bromide is 86.84 grams of lithium bromide. Okay, once again, I have 3 significant figures. So when I do this math of 25 divided by 159.8 times 2 times 86.84, I will get that I can make 27.2 grams of lithium bromide. Okay, so my thing that I need to look for is to find the limiting reagent. I need to look for the smaller of the 2, right? Limiting reagent, this is smaller. So my bromine is limiting. So So for A, my limiting reagent is my bromine. That is limiting. Okay, B, how much lithium bromide can I make? I can make 27.2 grams of lithium bromide. That's all I can make. Okay? How much lithium is left over? Now this, we have to actually do the stoichiometry. We're going to reverse this. So when I do this, I'm going to take the 27.2 grams of lithium bromide that I can make and see how much lithium it actually takes up. So I have, I need to go to moles. So in 1 mole of lithium bromide, I have 86.84 grams of lithium bromide, right? And in 1 mole of lithium bromide, I have 1 mole of lithium. And in 1 mole of lithium, I have 6.94 grams of lithium. Okay, so my grams of lithium cancel, my moles of lithium cancel, my lithium bromide cancel, my moles of lithium cancel, and I now have grams of lithium. So this will be how many grams of lithium it takes to produce that lithium bromide. So when I do that, okay, actually it's 2 moles, right? 2 moles of lithium to 2 moles of lithium bromide. It does reduce to 1. Okay, so when I do the math here, that means I've used up 2.17 grams of lithium making it. Now I started with 27 grams of lithium, right? So when I start with 27 and I use up only 2.17, that means I'm just going to take the 25 and subtract the 2.7. Let's see. And my computer is thinking again. So if I start with 25 grams, which I started with up here, way up here, and subtract 2.17, Come on. So 25 minus 2.17 leaves me with 22.83 grams of lithium left. Now, notice I only can go to the 10th because this 25 right here only goes to the 10th. Wow, my computer is taking a long time to think. So I will report this. There we go. So I started with 25 grams of lithium all the way up here. And I'm going to subtract the 2.17 grams that I use up to make this. Why does this do this? So that will give me 22.8 grams of lithium left. Okay. So 2.17 used. So that gives me 22.83 grams. But notice this only goes to the 10th, so I can really only go to the 10th. So I have 22.8 grams of lithium remaining. Okay, with my sig figs. So let's see. We did A, we did B, the mass of the excess reagent we've done. If 25 grams of the product is made, what is the yield? Okay, so we expected 27.2, but we only got 25 grams. So let's do the percent yield. Now remember, for percent, we have the actual divided by the expected multiplied by 100%. So the actual on part D said that we were able to get 25 grams of lithium bromide produced, right? But we were expecting 27.2 grams. So 25 divided by 27.2 times 100% gives us a 91.9. We've got 3 sig figs on both of these. 91.9% yield, which is a pretty good reaction, honestly. Most chemical reactions are in the 50 to 60% yield, so that's actually really, really a good chemical process. Chemical engineering is all about maximizing yield. So anyway, if that kind of thing is your jam, you might want to look at chemical engineering for a career. So have a great day, and we'll talk about limiting reagents in class. We'll see you later. Bye.